So we are recording, and okay. So this is our chapter. Let me see if I can just pull this chair. It's good. Okay, so that's our lecture. Lecture 1. Okay, so we have taught about this already in linear controls. X dot equals to f of any. So we are talking about a model now, right? The state space model. So we will be only dealing with state space model, nothing, no transfer function. Nonlinear systems does not have transfer functions. Okay, so it's all state space, pure x dot equals to f of x u kind of systems, right? So and y equals to h of x u kind of systems, right? So we have x is your state variable, which belongs to your Rn, means n variables are there in that vector. You have your output vector, which is again y is a m dimensional vector. Okay, so and then you already know that this x dot of f of x u can be expanded like this. Basically, this is first order differential equations. For each state variable, you want to know how it varies with time, right? For each state variable. So it's basically like saying x1 dot equals to f1 of x comma u, right? And x is again a vector, x1, x2, xn, right? So x is kind of a vector, x1, x2, x3, xn. Okay, so so similarly this can go up to xn dot equals to f of n x comma u, right? So that's the kind of systems we are talking about. So once you have the system, like whether you use Lagrange or anything, once you have this model, our work will start from here. Okay, so we will not focus on deriving models here. We will be given a model and we will work on it. And your model should be expressed in this state. You need to identify your inputs, right? Your inputs, which is u. U is your input. X is your states. And then you have y is your output, right? Once you identify this, you get this x dot and then y models. Okay, so here here's what we have. In fact, this system can be so so this x dot, generally we were writing always, right? This can also be a function of time. So we can always write t comma x u also. So if you remember time variant and time invariant, time varying and time invariant systems, right? If t is there, then it is a time varying system. So if you remember your linear system, you had x dot equals to a t x t plus b t u t, right? So if that is the case, then t comes here, right? Because it's also a function of time. So these are time varying systems, right? And right. So that's one case. So that's time varying. So we will be dealing with time varying systems also. And a system which does not have time into that is time invariant. And then there will be systems, if you remember, just with x. So they are called unforced systems or autonomous system. There is no input as such. And there is a reason also, right? Your u is all, you can choose, like in linear systems we used to choose u equals to minus kx. So it's basically a function of h of, or some gamma x, right? It's a function of x state. So that's why you can always deal with these kind of systems as well. So we can focus a lot of our time on this kind of system, or x dot equals to f of tx. No input involved, whether the system is stable, unstable, because u can always be chosen as a function of states. So basically it then becomes this, right? So that same stability definitions will come whether bounded input, bounded output, or the autonomous system is stable itself. So you already chosen u such that your system is stable, kind of thing. So we'll go over, and being because you've already taken modern control, life will be easier. All the definitions and everything kind of are same. Okay, questions here? So this kind of classification there, and now equilibrium point. You guys already know that. I like it once you have taken that class. Now I'm kind of. So equilibrium point is basically a point where x dot is of fx star or u star is equal to 0, right? Or any of this. Basically x dot has to be 0. Okay, so you have to solve for, if it does not depend on u, it's only just x star. And equilibrium point are of at most important in linear systems. It was not that important, but nonlinear system it is very. You will see that this is the like linear systems. There was no multiple isolated equilibrium points. Like if you see inverted pendulum example, for example, x dot equals to ax, right? What is the equilibrium point here? X equals to 0. So that is one, like you will not find equilibrium point which are separated. Sometimes it will be a line, but line is connected, or it. But in nonlinear system, for example, inverted pendulum, right? You can find an equilibrium point here, as well as the downside. So there are isolated multiple equilibrium points in nonlinear systems, and stability is the property of the equilibrium point. It's so interesting, like where do you start, which point you start close to, you might converge to a different equilibrium point, right? In nonlinear system, there was one equilibrium point here which is unstable, and one equilibrium point here which is stable. So the stability is the property of equilibrium point now, like where, so that will be an important aspect of it. So it's very important to first find out what the equilibrium point is, right? So you can always compare, like even if x dot equals to ax plus bu, you will see that equilibrium point, you can make it equal to 0, that is ax plus bu, and then you can solve for x and u. So your x star will change as u changes, but again, you will get a connected equilibrium point. And it means you will see that bu or ax equals to minus bu, right? And then, or you can say u star. So whatever you choose, you can solve for. If a is invertible, you can say x star equals to a inverse bu star. So you can see that it's one connected equilibrium point, not. But here in nonlinear system, it's interesting. There can be multiple stable equilibrium points. So if I'm here close to one equilibrium point, I will reach there. If I'm close to this, I will go there. And depending on you can change equilibrium points. If there can be, suddenly there are 2 equilibrium points, suddenly you change input, suddenly there become 3 inputs, 3 equilibrium points. So the behavior is really rich, interesting in nonlinear systems. Even number of equilibrium point changes, as we'll take some examples as we go along. But that's the important aspect. Okay, so that's there. So some of the interesting properties of nonlinear systems that I want to write, properties are like, we'll go, these things will make more sense when we go later in the course. Finite escape time, and then you have multiple like it can go to infinity in just finite time. Like this, we'll take some examples. Some states can go to, they're like, if system was unstable, it took some time, like x means as t goes to infinity or something, it will go. But here within, you can exactly tell you at t equals to 1, it will go berserk, right? So you can multiple isolated equilibrium points, and we'll take some examples and it will be clear. Okay, and then third, limit cycles. This was not like, you can get oscillations and so things can converge from like here, like on a trajectory, like a limit cycle kind of a case. So when you are outside this trajectory, you are attracted toward this. When you are here, you are so stable. So basically you converge on this, some kind of a limit cycle kind of behaviors, which is interesting aspect. Limit cycles are there. And chaos. So you can see chaotic systems in nonlinear. And bifurcation, like there is suddenly trajectory from stable to unstable, it can bifurcate. One goes to stable trajectory, one goes to unstable trajectory. So these kind of behaviors, bifurcation. So all these behaviors are not there in linear systems. They are in nonlinear systems. So will be, and you can see, like even in linear systems, all of our examples, mostly when we derived were nonlinear. Okay, so that's one case. Okay, let's take an example and see. So example is like our simple pendulum, right? So it's a simple pendulum, right? So we have theta here, we have L, the length of this, the mass M. Okay, so you can apply the Newton's second law, right? Second law, and say your inertia is equal to all the torques, right? Sum of all the torques. So in this case, it comes out to be ml squared. Let me see. ml squared theta double dot equals to your so we can write if one is a mgl sine theta minus kl theta dot. This is because of the friction, and this is again equals to external torque that you are applying here. Let's say I'm applying external torque. Okay, so this equation, so we have two states, right? We have theta, you can say your x1 equals to theta and x2 equals to theta dot, right? You can write your equations of motion using this equation now, right? So you begin x1 dot equals to x2 and x2 dot equals to this theta double dot that you can find equals to, it will be g by L minus g by L sine theta minus k by ml theta. So this theta will be what, x1, and this will be k by x2 plus t over ml squared. So this is your equations of motion, right? So going from there, so that is your f of xu, right? This is your f of xu. So now you can find equilibrium points if you want to see so equilibrium point will be x1 dot equals to 0. That means x2 equals to 0, right? So if x2 is equals to 0, that means and let's say your u equals to 0, that means there is no torque, so it will be minus g by L sine of x1 equals to, because x2 is 0, then equals to 0, right? Now you can see there are, where can this be 0? At x1 equals to 0, right? And x1 equals to pi. So anything like, I can say that x1 equilibrium is basically plus minus n pi, where n is equal to 0, 1, 2, whatever, right? So basically lots, or you can say at least two equilibrium points are isolated also. They're not connected. One is here and one is at the bottom of it. So that's like multiple equilibrium point, right? You can write your x to be x star equals to n pi, where n equals to 0, or you can say plus minus 1, plus minus 2, and 0. So this is your equilibrium point, and it is isolated. And when you do the stability analysis, we will find that one is stable and one is unstable. Okay, so that's one case. Questions on this? So now another example. It's called tunnel diode circuit. Again, not aerospace related, but doesn't matter. We are studying nonlinear controls here. It does not have to be just mechanical systems, right? So let's let me draw a circuit here. Capacitor. So it's a tunnel diode circuit, and this here, let me say there is a current here, I can say IR. So current in this circuit here in the diode is IR, okay? Current here is IC in the capacitor. So this is a capacitor, this is a diode, and this is an inductor coil. So there are three main components in any circuit. Your computers or any laptops, they are made of three main elements. One is R, resistance. L is your inductor coil, and capacitor is okay. So based on that, you can design circuits to provide you, whatever you are. Let's say I want a constant voltage at output all the time, or whatever, right? So and this is your input E. So your input is this E, and IL, voltage across this is VL, across the inductor, voltage across capacitor is VC, and voltage across resistor is VR. Okay. And this tunnel diode has a characteristic. So current is passing. Again, you don't have to know this stuff. I'm just saying that when this current IR passes through this diode, right, there is output voltage across it. So when a current passes through this diode, you get a voltage across. When you take, have you seen multimeters, like to measure? So you have two things, right? When you put those two sticks plus minus, it will read a voltage across resistor. So what they are saying is the voltage looks like this. The characteristic of this I versus V looks like this, something like this. Okay, so this is I equals to, in fact, I was telling opposite. So the voltage that you apply, your IR is the output. Okay, so your I flowing in this diode is a function of this voltage like this, and it's a nonlinear curve, right? So some basics, your IL. What is IL? IL is the current flowing in the inductor coil. That is given by C. Sorry, I'm talking about this IC here. So current flowing in the capacitor IC is C dVc by dt. So you know the voltage, you take you differentiate with respect to time, multiplied by C, you get your IC. These are standard electrical things, so you don't have to. And similarly, your VL across the inductor, the voltage across the inductor coil can be found out by L. So L and C are the like parameters of the capacitor. So this is the capacity of the capacitor C. You will be a resistor of 2 ohms, capacitor. So they have units, and then you will have. So this will be L d IL by dt. Okay. So these are two relationships known to us. And then you apply Kirchhoff's. Have you heard of Kirchhoff's current law, Kirchhoff's voltage law, maybe in your undergrads? Long time ago. Don't worry. Again, as I said, we are just modeling right now, and modeling is not important here. Somebody will give you a model or something, but we apply Kirchhoff's current law. Okay, it says that, in a loop, so these are loops. If you see this loop here, this loop here, it makes a loop. Okay, so sum of all the currents in a loop is 0, always 0. Where you miss, that's Kirchhoff's current law. Okay, so when we apply the current law in IC, so here at every node, sorry, not just loop, but current entering at a node, sum should be, it's standard, right? I don't know why he gets so much attention, but current entering should be equal to out. So that's exactly Kirchhoff's current law. So at this node, if we say your IL, so IC, what is entering? IC is leaving, IR is leaving, right? So at this node, and IL is entering. So if you see arrows notations, these two are leaving, right? So they are considered, let's say, positive. Leaving is considered positive. So IC plus IR minus IL equals to 0. So that's your Kirchhoff's current law. Okay. And there is a Kirchhoff's voltage law also. So that's the loop thing. So current law is applicable for a node, and voltage law is applicable for the loop. So the Kirchhoff's voltage law, again, this is like Newton's law for electrical circuits, right? Newton says F equals to ma and all that jazz, right? Force has to be. So Kirchhoff's voltage law says that voltage in a loop, which is in this loop here, VC. So you read like this. This thing should be read. If you go from minus to plus in the loop, so this is minus, this is plus, right? So it is considered negative, and when you go from plus to minus, it is considered positive. So it will be VC. So that's plus to minus, then minus to plus, minus E plus and this has some where is the resistor? So this has some resistance, right? So it becomes RIL. So voltage across a resistor is resistance into that current flowing plus VL, right? I think there should have some resistance here somewhere, but for that is R. But anyways, so that's one equation. We have these two equations now, right? And now we can put, because our states are, in this case I'm saying, let's choose our states to be x1 to be Vc. So voltage across the capacitor is one state, and current across the inductor x2 is IL is one state. I chose those states because if you know those two, you can define everything else. That's the basic idea. Again, if you remember states, number of states are same, but you can always choose different states. Okay, but let's say we choose these states. So in this case, I need what? I need x1 dot to give equations of motion. What do I need? x1 dot, right? So that will be Vc dot. So we need find Vc dot, and x2 dot will be IL dot. If you remember, this here will be Vc dot, right? And this here will be IL dot. So we can use these two to get the equations here. So if I just plug everything in, I will get this equations here. x1 dot equals to 1 over L x2. x2 is this, IL, minus 1 by C h of x. Okay. And h of x comes from this, right? Because this here, IR here is x, or I would say, what is that? X is the voltage across the capacitor, Vc, and that is x1, right? And then x2 dot will be 1 over L. Just nothing but plugging these things in these equations and then solving for Vc dot and
that voltage equals 0 on the right hand side?
yes.
Okay.
Okay, so 1 minus x1 R over L x2 plus 1 over L u. So that is our x dot equals to f of x u. That is our equations of motion. See, the idea here, we wanted to derive this equation. Now you want to find out the equilibrium point here, right? So just wanted to show the interesting characteristic of the equilibrium point here. Okay, so if we solve for equilibrium point, that will be 1 is x1 dot equals to 0. So now we are finding equilibrium point, and that is x1 dot equals to 0 and x2 dot equals to 0. So from there, make it equal to 0 and equal to 0, and we can solve for this equation here. And let me show you how. So in this case, if we make this equal to 0, let's say that everything is L, so L goes to 0, right? So it becomes minus x1 minus rx2 plus u equals to 0, right? From the second equation. So that basically gives you u equals to x1 plus r x2, right? So that's one equation. Now from here, I think we can solve for x2, right? So that will be, so in x, sorry, there is a typo here. There should be c here, both c. Okay. So from there, what will be my x2? My x2 will be basically h of x1. Right? So that I can plug in here, and that becomes now my u equals to x1 plus r of h of x1. Okay, So that gives me that u. So now I can solve for now. So basically I'm solving for, so my h of x1 now can be, say everything is, so we are trying to solve for, because h of x1 is x2. So now I can solve for, if I, once I find that, so let's say my h of x1 will be equal to what? It will be u by r minus x1 by r. Correct? So this is equation here, and it's a equation of straight line if you see in terms of x1. No? Y equals to mx plus c, right? So this can be, what are the straight line equations? Y equals to mx plus c, right? So this can be mx. So basically 1 by r is a slope, right? And this is a constant. U by r is a constant. Given an input, that is a constant. So now let's see, because, and now what will be the solution? This h of x1 is already given to us here. So we already have h of x1 here, and the equilibrium point, that line is coming straight line. So that means the intersection of that straight line and this curve will be the equilibrium point, right? See, h of x1 is a curve here, but this is a straight line. So the solution will be the intersection of this straight line and the h of x1 curve, right? So let's draw that again. Let me draw that again here. Let's use some different color. So let's say this is my curve, and I already have this this h of x1 thing, right? And let's say this is I, this is V, and this straight line here, like let's say this straight line, depending on, so this straight line here, right? So this is slope, 1 by r is the slope, right? So how much tilted that line is given by 1 by, so if r is constant, then slope is constant, no problem. And what is c? Do you guys know what is c in a straight line? So this y equals to mx plus c basically is like c. So the intercept, right? This intercept is what the slope is constant, because if 1 by r is constant. So if you see, if my slope is like this, then I have one equilibrium point. You got it? So if because that slope is chosen by u by r, that is e by r. So I can give more voltage, and if my curve is right here, then I have 3 equilibrium points. So you increased the input, and you got 3 equilibrium points. Interesting. Like I haven't seen that in linear system or anything. That's the beauty of a nonlinear system here. That just by changing the input, you change it changes the total behavior. Which equilibrium point be stable and all that stuff. When we do the stability analysis of this 3 equilibrium point, you will realize how interesting that happens. That suddenly, just by bumping up the voltage up and down, you can change the number of equilibrium. That is unheard of in linear systems. That's the beauty here. Like you can get so many interesting behaviors. Like let's say it was converging to a point, and then say no, I want it to converge at some other point, or you can just change the voltage and this curve here. Again, it becomes 1 to 2 depending on where. So Q1, Q2, Q3. All you have to do is solve this equation, and you will get the number of equilibrium points. Right. So that was the multiple isolated equilibrium points you can get in nonlinear systems. That was the point of this example here. Okay. Questions on this? Any questions? Okay. And again, this will be, as this is more theoretical, we will be implementing a lot of things as we go along, but now we have more of philosophical, theoretical discussions supported by mathematics will be happening throughout, and we'll be taking a lot of interesting examples Questions?
I got the concept, but I missed somewhere in the derivation. So is there any difference?
Yeah, I mean, so it's the whole thing. I'm exactly following the lecture notes all, and this example is also in the book. Okay, chapter 1, I think. So the derivation, as I said, it's simple. You're putting. So IC is this, right? So you put this C dVc by dt. So you can solve.
So and that adds x1.
Uh-huh.
So about the adds x1.
Mm-hmm. Oh, this h of x. This is not derivation. It is given to you. So you buy a diode, right, from market, and they give you this characteristic. This is how it behaves. This diode, they give you a characteristic equation that this is how this diode behaves. It increases, and after this point, suddenly the voltage will drop, and so this is the characteristic of a diode that you have put in your circuit. Okay, so this h of v, that function will be given to you. Right now we are saying this is a general function, but this function, this curve will be given to. So this is yeah. There is no derivation involved here as such. It's saying that I have a diode. They might have done lots of experiments and to get this h of v or whatever the circuit is. So okay, that's the b. This is a component that you bought, and they give you, say, okay, you apply this much input, this is the voltage, this much current, this is the voltage, this much current, this is the voltage. Basically, they give you a curve. If your current is this much, your voltage, opposite. If your voltage is this much, this is the current. If their voltage is this much, this is the current. So this is the characteristic of the tunnel diode that you have put on here. Okay. So that's not an issue. Okay, that's why I hate this 50. If I take another example, start another example, it might go over. But yeah, and so keep reading these notes. In next class, we'll do some more examples, which specifically shows these properties. Okay, all type of different nonlinearities, and so do chapter 1 reading in. So these chapters were designed for a 80-90 minute class, right? So you will see that we might take 2 classes to finish 1 chapter in the notes here. So read until chapter 1, and then we'll start chapter 2 also in the next class, where basically we want to analyze smaller systems, second order systems first. Again, linearization is still as a good approximate tool in nonlinear systems as well. It gives you a behavior, at least at near the equilibrium point, what will be the behavior you can get through these systems. And then we will be doing some phase plots and like drawing pictures, like instead of exactly solving. So these are what are these here? If you see, what is this? These are first order differential equations, right? This first order differential, to simulate or to get x1 of t or x2 t, what are you doing? You're solving the ordinary differential equations, right? What was the point I wanted to make? Yeah, so, and these are hard, like solving ODEs for nonlinear system. It's not like xt equals to e to the power at into x0, right? It's not that not anymore a simple solution like this, right? That was the advantage of linear system, that you have a closed form solution of ODEs. Doesn't matter what is the size of state and all that. Here, no. So what do? You basically approximate. You can draw some pictures, phase plots to any nonlinear kind of system, which gives you kind of behavior of how these systems will behave when you are here, So that's a very powerful tool to analyze at least initial part of the system. Okay, at least for second order nonlinear systems. Okay, and linear analysis kind of give you behavior around that equilibrium point. Okay, so let's say this is equilibrium. You go straight lines will be, so whether you will be converging in straight lines or whether you'll be converging in a spiral mode or something like that. That can be analyzed using linearized system, whether I'm converging as straight lines or I'm spiraling. System is stable, right? I'm saying the curve doesn't matter where you start, it goes to the origin. That's one statement I make. Now, how it goes to origin depends on the eigenvalues of the linearized system, whether I go straight like this or should I spiral in, or those kind of behaviors can be studied using the linear analysis there. So that's what will be. It's still 2:20, right? What time class ends?
I think it's 6:20.
Yeah, so right on time. Yeah, as I said, I'm not used to 55-minute classes, so it kind of breaks the momentum. But anyways, and at the we will help. I think we can do one help session also. It's 3 of us, so we can organize one help session once we start giving homeworks. There. Okay, so I think I've recorded this, and I will.